I've had quite a varied engineering career, probably over the last 40 years. I think I got my first soldering iron at the age of 5, and having picked it up at the wrong end at that age, you don't do it again. Around about that same age, I was poking around with bonfires, and I probably started an enduring relationship with combustion and thermal energy. And when I was thinking about this this presentation, I was thinking that it's really just in maybe the last 150 years or so that we have had radically new forms of energy, electricity, direct current, alternating current. Prior to that, we had renewables, and we put a lot of emphasis into thermal energy. We lit fires to keep warm. We made blast furnaces, smelters, kilns for reducing metal ore down to first copper, and then copper and tin to make bronze, and then iron. And, you know, you can look right back to the 6,000 years of human history where we have been using fire to do useful work for us, smelting metals. And then our human relationship with fire probably goes back 10,000 years, 100,000 years, maybe even longer. So the subtitle for this is 10,000 Years of Unfinished Business, and also canned heat. I'm going to talk about ways in which you can tame fire to make it do what you want it to do, not what it wants to do. Finally, an Edwardian idea tamed by 21st century open source microelectronics. Okay, almost exactly 5 years ago to the day, I found myself short of a job, which I'd been doing in about a quarter of a mile up the road, and I didn't have much on my plate at the time. And I heard about an organization in Berkeley in Northern California who were doing interesting things with wood gasification. And so I jumped on a plane and I hung out with those guys for a week or 10 days. And I got involved in converting an old diesel engine so that it would run on wood gas. And it took all weekend, and we used an Arduino to run the spark ignition system. And of the various projects that was running at this weekend workshop, it was the only one that actually ran at the end of the allotted time. So okay, this is gasification 100 years ago. Almost exactly 100 years ago. Gasifiers were, this is the gasifier here, and you can tell from the size of the step ladder up the side of it that it's quite a large machine. And these would run on either coal or woody biomass, such as woodchips or crushed nutshells, rice hulls, coffee husks, lots of agricultural byproducts that you couldn't eat and you just had to dump. You could run through one of these, and using the wonderful chemistry of carbon, you could create a mixture of primarily two flammable gases, which are hydrogen and carbon monoxide. And these two gases, although they created a gas of very low energy content, about 1/6 of that compared to natural gas, you could mix this gas with an equal volume of air, and you could run a large gas engine, such as this one. And then this tall tower in the middle is effectively a gas scrubber, which does two things. It filters the gas, it removes any dust particles that would upset the engine and the valve gear, and it also cools the gas back down to ambient temperatures so you can get as much gas into the engine as possible. So this is literally 100 years ago. Then moving on, I was down in Amberley Chalk Pits Museum just before Christmas, and here is almost the identical gasifier unit and scrubber unit, and behind here, which you can't see in this picture, is a very, very similar sized gas engine. So this is 100-year-old hardware. Okay, so the basics of biomass power. You take woody biomass and you convert it by a process of thermal decomposition into a mixture of flammable gases. And this is sometimes called wood gas or syngas. You can fuel a conventional spark ignition petrol or gasoline engine with this wood gas, and it can then be used for power generation, mechanical power, transportation, and you can have a very conventional spark ignition generator set that are available worldwide. Okay, so gasification, it was first studied properly in the 1840s by Gustav Bischoff. Prior to that, a lot of research into combustion and the chemistry of carbon had been done by the metallurgy industry. Hot carbon is great at reducing metal ores down to their metallic elemental state, and so it was people that were in the metal industries, and also even the village blacksmith knew a lot more about the chemistry of carbon than most people today. Converting a solid fuel into a gas is a great way of making it more useful. Solid fuels are hard work. You've got all sorts of problems like mechanical handling problems, storage. They often don't produce a consistent thermal output. But if you can convert, let's say, woody biomass into a flammable gas, you can then pipe that gas into a secondary combustion zone, and you can burn it with the right ratio of preheated air, and you can get a very intense flame from it. Conversely, you can pipe it into the air intake of a regular petrol engine, mix it with the right amount of air, and you can run the engine on it. Now, during World War II, when hydrocarbons were in short supply, there were a lot of acts of desperation to try and maintain public transport and personal transport, and a lot of vehicles were converted, particularly in the northern countries of Europe, Scandinavia, Germany, Poland, Austria. They were converted in really quite large numbers by the mainstream motor manufacturers of the day to have a gasifier on them. Audi and I think it was MAN trucks were producing wood gas powered trucks off their production line for the German army from about 1941 onwards. In total, there was 1 million vehicles converted in the whole of Europe. Now, how far can you drive a truck on wood? Well, We were talking about energy densities recently, and if you take a 15-inch length of 4x2, and I'm sure we all know what 4x2 is, there's enough energy in that to drive a 2-ton pickup truck a mile. So about 900 grams of wood will produce about a mile in a pickup truck at, let's say, 55 miles per hour through the gasification process. So any hydrocarbon fuel can be converted into this low-energy gas using the process of thermal decomposition. Now, I said earlier that this is the art of taming the combustion process so that it yields intermediate byproducts of combustion that are useful, rather than fully oxidizing those chemicals and producing just heat and carbon dioxide. So it's like taking out what you need from the thermal process before the fire has a chance to fully consume those products. So basically, the gasification process involves burning, let's say, wood chips in a oxygen-reduced atmosphere. And you have a reactor vessel that's about the size of that waste paper bin, and you put biomass in the top, and about a third of the way up from the bottom you have air nozzles going in, and those air nozzles will draw air in to a combustion area, and you're only putting about 25% of the air required for 100% combustion. And this means that only 25% of your fuel will be fully combusted, creates a lot of heat, and the remaining 75% of your fuel will be thermally decomposed into the flammable gases that you want. Gasification is a tricky process to get right. You have to firstly get your gasifier running optimally so that it produces good quality gas, and given half a chance, they will just try to fully combust your fuel stock. And secondly, you are running a petrol engine on a gas that is not really of a very consistent calorific value. And so the best way to deal with this is to put some simple electronic controls in there to control the amount of air that's drawn into your gasifier, and also to control the mixture of the gas and the air that goes into the air intake of your engine. So it's a perfect candidate for automatic control. Okay, chemistry of gasification. I think I've said most of this. Wood gas is effectively, the best way of thinking about it is when you're having a tidy up in your garden in the autumn and you've got a bonfire going, and you pick up a whole bunch of leaves or dead wood or whatever, and you dump it on the bonfire, and it smokes with horrible yellow, green, mucky, brown smoke for about 2 or 3 minutes, and then all of a sudden it goes whoosh like that. Well, that horrible green stuff, that is the tars and the volatiles coming out of the biomass. You have effectively choked that fire. You are running it at a oxygen-depleted state. It's running very, very rich, and when you run any thermal process rich, you get a lot of unburnt volatile matter, or even unburnt hydrocarbons. And then as the thermal decomposition process increases and that overload of damp fuel reaches the optimum temperature, and you have more oxygen reaching the horrible yellow smoke, you get the right fuel-air mix for the smoke to burn, and all of a sudden you get an almost explosive flare-up. Well, that is the wood gas reaching its optimum stoichiometric mixture. and it's something that you see if you run a wood stove or a bonfire in your garden. You see that quite often. Okay, so the way in which it works is first in the reduced oxygen atmosphere, carbon is partially oxidized to carbon monoxide. Carbon dioxide is passed over hot charcoal where it picks up another carbon atom and it becomes 2 lots of carbon monoxide. Water vapor, which is either because your wood chips are slightly damp or there is chemically locked water within the lignin and the cellulose of the structure of the woody biomass. That is released, and that is reduced by passing, by that time it's superheated steam, and it passes over the hot carbon bed within the gasifier, and that forms hydrogen. Good old nitrogen, that just goes straight through and just picks up a lot of heat. And the energy content is anywhere between about a fifth and a tenth that of natural gas. Here's a vehicle from the early 1940s. It's got a gasifier built on the back, and you put your wood chips in here. Now, one thing that isn't widely known is that there was a whole industry in Germany cutting up pine forests to make little cubes of highly specified standard fuel wood. And there were probably about 2 centimeter cubes, and dozens of factories had wood processing machinery that was putting pine trees in and getting 2 centimeter cubes out. And garages that had been selling petrol were then selling wood chips, wood blocks. Anyway, you put your blocks in here, you light it, you give it about 5 minutes to heat through, and then you crank your engine over on the battery and it draws the wood gas through the top here. And as the engine produces the suction, it draws atmospheric air in through here, in through some air nozzles into the bottom third of the gasifier. And the gas is not stored, it's burnt in the engine within a few seconds after it's been created. Wood gas is not a particularly stable gas. It breaks down into its original forms. You can't store it and you can't compress it for using it later. So it's a kind of on demand. It's produced just in time. Here's the inside of a gasifier. You put wood in the top here. C is your air inlet, and you have a series of radial nozzles that point into the center. This area B is called the hearth. Then you have a restriction, sometimes called a throat, which is D, and you get red hot carbon chips building up in there, and that's your reduction zone. And so the products of combustion, which are the smoke, the volatile hydrocarbons, are all passed through an orange hot bed of incandescent carbon. What comes out of the bottom, out of D, is very hot, 900 degrees C, very dusty, carbon-filled wood gas, which exits through E, goes into what looks a bit like a Dyson vacuum cleaner, which is a cyclone. Your carbon and dust particles end up in a collection vessel here, and the hot gas comes out of G, goes into a radiator cooler that was often put on the front of the vehicle, so it had the airstream blowing over it. By the time the gas comes out of here, it's about 100 degrees C. It goes through what we call a packed bed filter that is basically just a dustbin full of different layers of finely divided biomass like sawdust. And then it passes out of your final filter into a mixer arrangement here, and you've got 2 butterfly valves. L1 is controls your mixture. Wood gas, by a stroke of coincidence, mixes about 1:1 with atmospheric air to produce the correct stoichiometric ratio. And so the valve L1 makes sure that you have the right mixture. And then L2 is like the throttle valve in the top of your carburetor. Open up valve L2 and your engine will rev a lot harder. So that's basically what any gasifier system has. Now, you need all that to bolt on to an existing generator set before you can do anything. And that little lot is 2 vessels about the size of that waste paper bin, and what's not shown on the top here is a wood chip hopper, which consider it to be something like a standard 210-litre oil drum. 210-litre oil drum will produce about 24 kilowatt hours of electricity. Okay, right, automating the system. Mechanical handling, we need an automatic fuel feed auger to add the wood chips into the top of the gasifier. At the bottom of the gasifier, we need something that shakes the grate, removes the dust and ashes, and makes sure that you've got good gas flow out through the bottom of the gasifier. Temperature monitoring, you need probably about 3 thermocouples capable of 1300 degrees C operation in order to monitor the temperature at the top of the reactor, the bottom of the reactor, and preferably the gas temperature as it goes into the engine. Pressure monitoring, if your gasifier becomes blocked with charcoal dust, it will have a greater pressure drop across it. And we use some simple machined silicon beam pressure sensors so that we can work out the pressure difference across the gasifier. And if the pressure ratio across the gasifier appears to be increasing, we shake the grate to try and relieve the blockage. When you start up the gasifier, you've got a lot of yellow smoke to get rid of, and so we normally put that up the exhaust pipe, and we have a high temperature heating element that will automatically ignite those noxious gases and flare them off until we get good engine grade gas. We've got blower fans, we have a lambda sensor so that we can detect how rich the engine is burning, what excess oxygen is left in the exhaust, and from that we then use that to control the mixer valve. And the air gas mixer valve, we run a PID loop and have a model radio control servo move that for us. Okay. Here's a system I've been working on, which is installed in a property down in Kent. This is the wood hopper, this is the main filter, electronic control system, engine is over here, and this is 4 tons of water, which is acting as a thermal store. Right, the IC engine, it's an off-the-shelf, globally sourceable engine, 3 litres, 1500 RPM, about 40 horsepower. It's got an electronic governor for maintaining 1500 RPM. We monitor the oil temperature and coolant temperature and the oil pressure, so we can shut it down if we detect any problems. We have a conventional starter and conventional electronic ignition, and this engine will produce approximately 20 kilowatts of electricity and about 60 kilowatts of heat. There's the engine. It's an old GM truck engine, a lot of old cast iron. Okay, this is the state of the product that I was working on out in California. I was responsible for this little bit here in the middle. Let's get on to that. The generator, off the shelf, synchronous generator. Great complement for solar PV or wind. Your wood chip generator will run when you don't have the other renewables and providing you've got wood in the hopper. Right, sensor and control challenges. Yeah, I mentioned thermocouples running it up to 1300 degrees C. We need a thermocouple amplifier and linearization for those. We're doing multi-channel pressure monitoring. We're running a PID loop to run a servo valve. We've got multiple DC loads, a bit like a regular car. We needed a user interface, which was an LCD and some menu buttons, turnkey operation, safe controlled shutdown, cost sensitive and open source using components that could be sourced globally. We chose to use basically, as they say in the States, leverage off the Arduino ecosystem. We already had a microcontroller board, which I'm going to pass this around so you can see it in the flesh. This is effectively an Arduino Mega that's got a lot of temperature and pressure sensing channels on and a whole lot of other stuff. That's it there. And I then had to come up with a means of interfacing that board to the rest of the systems within the Gasifier. So I came up with an idea for a relay board, which I shall also pass around. This is an unpopulated one, designed in EagleCAD. It's about a 10-inch square board, cost about 60 quid in small volumes in the States. It accepts standard automotive plug-in relays. It drives a lot of 12-volt loads, 0.2-inch pitch power connectors, so the thing is easy to wire up. So that was that, and that's it populated before the red board sits down on top of that. Okay, the future. The Arduino Mega is looking quite old hat these days. I think we've all more or less made the transition towards 32-bit ARMs, which are fantastic value. 16 and 24-bit A to D converters are now commonplace and cheap, and very often there are 16-bit converters built into your microcontrollers. We've moved away from the 4-line character displays, color TFT graphic displays, 2.8, 3-inch diagonal are now only about £8. We're doing a lot of web and cloud-based monitoring for remote control, remote access, Wi-Fi and low-power wireless for remote control of these systems. That also has come on in leaps and bounds and is very cheap. Higher resolution monitoring and better control from a processor that can rattle along at about 20 times the throughput of the humble AT Mega. And also, with all this high tech, we can also do a low-tech solution for developing village-scale power, which is this. This was the one I worked on in 2010. This is a Lister diesel engine that we converted to spark ignition. These are still made in India. They cost about $250. We've got a water cooling tank here. We've got an alternator, belt drive. This is the Gasifier, the fuel hopper, the filter barrel, and the hot gas out of the exhaust of the engine comes up through this insulated pipe and pre-cooks the wood chips before they drop into the Gasifier. And so we recuperate a lot of the thermal energy. Right, I'm going to try and leave 5 minutes for questions. I realize I've had to get through a fair bit. Okay, we also do a larger size. Here's the Gasifier. That is a twice scale version of the one in the previous slide. This is a 6-meter shipping container, and we've got an 8-liter Cummins diesel engine lurking in the back there. And this 3-meter section of shipping container is the fuel hopper, and all power labs, and these can be used to reinforce the grid in remote areas. So this was developed during the time I was there. I'm personally responsible for wiring up some of this. And the great news is that All Power Labs, after 6 years of being a startup, now have got some cash like they didn't have when I was there. Right, a couple of workmates of mine, they are sitting in the hopper of that 100 kilowatt machine. And there's room for about another 3 there. So all the usual thanks. And that's it. Okay.